Stop accidentally training on your test set. Tune with GridSearchCV, the leak-proof way. By the end, you will know how to tune model settings without letting validation or test data give your model a secret advantage. I'm Professor Pi, teaching AI foundations with simple Python. Hyperparameter tuning is how we pick the recipe that makes a model work best. The problem is familiar. You run many experiments. You fold data and score performance. If you let pre-processing or statistics sneak across folds, your scores become lies. Success looks like a model that performs similarly on a fresh held-out test set and in cross-validation. That reliability matters when you move from toy data to real users or production. At a high level, the fix is simple. Never compute anything on data that will later be used as a validation or test example. Fit scalars, encoders, or feature selectors only inside each training fold. Then, tune hyperparameters on that honest cross-validation. The honest score tends to be lower, but it is trustworthy. It tells you whether changes generalize. We will build a tiny pipeline to demonstrate the full flow. First, we create a clean baseline. Then, we show a leaky example so you can see the illusion. Next, we show a safe pipeline, then a safe grid search, and finally, we verify on a held-out test set. This will make the code feel like a simple sequence of safe steps before any complexity arrives. First, we build a clean baseline. This snippet builds a tiny, trustworthy baseline with scikit-learn, the function make classification, which creates a reproducible toy dataset, produces a matrix X, and labels Y using a fixed random state. The function train test split, which separates data, holds out a clean test set, so nothing from testing touches training. A logistic regression model is fit only on the training split, and the model score method reports accuracy on the untouched test split. This simple split is your ground truth reference for performance without any tuning. The printed test ACC is the first signal of how well a no-frills model generalizes. And it matters, because we will compare all future tuning against this clean baseline. Next, we will intentionally leak information to see the effect. This snippet intentionally shows how information leakage sneaks in with scikit-learn. StandardScaler is fit on the entire training matrix XTR before any cross-validation. StratifiedKFold creates 5 shuffled splits for cross-validation. The code then calls cross-val_score to evaluate logistic regression on each fold. But because scaling saw every row in X during the pre-processing step, statistics from the validation fold leaked into training. That usually inflates CV leaky, making the model look better than it really is. Increasing N splits can amplify this illusion because each validation part becomes smaller relative to the pre-computed scalar. The printed CV leaky hints that this number is optimistic and cannot be trusted. Now we fix leakage by enclosing pre-processing inside the pipeline. This snippet prevents leakage by moving pre-processing inside the scikit-learn pipeline. The pipeline chains StandardScaler and logistic regression, so that each fold in cross-validation independently fits its scalar using only the training fold. The same StratifiedKFold object defines the splits, but now cross-val_score calls fit on the pipeline per fold, ensuring isolation between train and validation. The variable score is a more honest estimate and may drop compared to the leaky result because we removed the unfair peak. If you increase N splits, you might see slightly more variance in CV safe. The printed CV safe is your trustworthy cross-validated accuracy. Next, we tune hyperparameters without opening the door to leakage. This snippet performs safe hyperparameter tuning with scikit-learn's GridSearchCV. The grid maps the logistic-regression step named M to its regularization strength C using the key M_C, so GridSearchCV can adjust that step. GridSearchCV evaluates each candidate value using the same StratifiedKFold, but because we pass the pipeline safe, the scaler is fit only on the training portion within each fold. Calling fit on GS searches all options and tracks the best params and best score. Larger C weakens regularization and can fit training data more tightly, sometimes improving fit, but risking overfitting. The printed best C shows the chosen regularization level found without leakage. Finally, we refit the winning pipeline and check against the untouched test set. This snippet finalizes and verifies the tuned model in scikit-learn. The attribute best estimator returns the winning pipeline, already refit on the full training set with its best hyperparameters. We generate predictions for the held-out XT and compute accuracy by comparing YFAT to YT. This number is the only reliable performance check because the test set was not used during cross-validation or grid search. If you expand the search grid or add more hyperparameters, expect longer tuning time but potentially better generalization. The printed final test accuracy confirms how the tuned leakage-safe pipeline performs in real use. Map to a real project. Run the same safe pipeline on a customer churn dataset or a fraud detection set. Keep the final test set strictly offline until the very end. The same steps scale to larger data or more complex models with the same rule. Fit pre-processing only on training partitions. Recap. What it is: a leakage-safe tuning workflow that nests pre-processing inside the model pipeline and uses cross-validation correctly. When to use it: whenever you tune hyperparameters or pre-process features before model selection. One caveat: honest estimates are often lower than leaky ones, but they reflect true generalization. Next step: extend this exact approach by expanding the grid to tune the regularization strength and one other model hyperparameter. Then measure timing and validation variability. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.